Swayam Prabha. Digital India. Educated India.
In the last lecture, we are discussing about the energy transfer, and specifically we are discussing about the non-radiative energy transfer process. So, in the non-radiative energy transfer, what I showed you that D star is present and which is interacting with A, and this energy is transferred from D to A star. As a result, D is getting deactivated and A is now in the excited state. So, if I now tell you this molecule D star as one electron is over here, another is over here, and this A is present, A is in the ground state, then the situation is that these two A and D are actually interacting over a distance, and which is converting this A, this D as deactivated, and A is now in the excited state. And I said that before this dipole-dipole interaction, the interaction which is responsible is a Coulombic type of interaction, and then again I showed you that equation here, this K E T can be written as this kappa square divided by tau d r to the power 6, right, and then some constant like this way. And I said that this kappa square is where this r equal to distance between donor and acceptor, and this should be tau is 0, and then kappa square is my orientation factor. This kappa square depends on the relative orientation of the donor and acceptor. And if you look at the specific form of this kappa square, let me draw this donor and acceptor, these dipoles like this way. Let us say this is the donor dipole oriented in this fashion, and this is this acceptor dipole is oriented in this fashion, and this is the distance between donor and acceptor. So, this is my D, this is my A. Now, if you extend this line, the line connecting the D and A, and then you measure this angle, the angle between this line and the acceptor, and in this angle let us say is theta A, and this angle similarly is let us say theta D, and if you make a plane with this donor dipole and this line, the line connecting donor and acceptor and donor dipole, with this if you make a plane and the acceptor dipole and the line connecting the donor acceptor, with this if you make another plane like this, then the angle between these two plane, let us say termed it as theta t. So, this kappa square actually depends on these 3 theta values with this form as kappa square equal to cosine theta t, right, minus 3 cosine theta d into cosine theta a and whole square. So, this is my expression for the kappa square. Okay, let me give you 3 different examples, right. So, let us say case 1. Let us say this is my donor dipole and this is my acceptor dipole, right, and the distance between them is r, right. So, that is my distance, but that kappa square will not going to depends on that distance, it will only depends on the orientation, but total KET value will obviously depends on the distance. And you note here that dependency of this distance is 1 over r to the power 6, little change in r will change the KET value enormously, right. Okay, I will come later, I will tell all those things in detail. So, in this case if I tell you that what is the value of theta a, what is the value of theta d and what is the value of theta t, what will be your answer? Theta a is equal to 0, theta d equal to 0, theta t equal to 0. So, for these values of theta, kappa square will be equal to cosine 0 minus 3 cos 0, right. So, this will be equal to 1 minus 3, so minus 2 square, so is equal to 4. I will take another case, case 2. This is my acceptor, same distance r, sorry, this is my donor and this is my acceptor. For this case 2, I will also have different values of theta a, theta d, theta t. So, theta a is equal to 90, theta d is equal to 90 and theta t here will be equal to 0. So, in this case kappa square will be equal to 1, right. Okay, let me show you another case which is case 3. In this case, let me take my dipoles, this donor and acceptor, like one is like this is my donor and this is r, right, and this is my acceptor, such way that theta a is equal to 90, right, theta d is also 90 and the angle between these two is also 90 degree, right, and this will going to give me kappa square equal to cosine 90 minus 3 cosine 90 and cosine 90, right. So, this is going to be equal to 0. So, you see, depending on the orientation of these two dipole mu d and mu a, the value of kappa square actually varying a lot starting from 4 to 0, and that is the problem. Suppose you think of a situation, you have the donors, right, and how these donor molecules will orient in the solution, that will not going to depends on anything, because as we have already seen in the fluorescence anisotropy during our discussion on fluorescence anisotropy, that the orientation of these molecules in a solution is random. That is called the isotopic orientation. That means, the donor molecules will orient in all possible conditions. Similarly, the acceptor will also orient randomly in all possible orientation. That means, the theta A, theta D, theta T, the values of theta A, theta D, theta T could be anything, right. So, because of this isotropic orientation of the donor and the acceptor for solution, but for a rigid system like a biomolecules. Okay, I will talk to the I will talk about this biomolecule later on, but it is for sure that for a solution state, that the orientations of the donors and acceptors are random and is isotropic in nature. So, better to have a case 4 where I will take these randomizations of the donor and acceptor. So, for this case 4, what I have is the donor and acceptor are oriented randomly. This is isotropic, right, orientation. In this case, kappa square is written as the average value, right. So, I will integrate 0 to pi cosine theta t minus 3 cosine theta d cosine theta a square d theta t d theta d d theta a, and normalize it with 0 to pi theta t theta d theta a. And if you know the value of this integral is very simple, which comes out to be 2 by 3. Now, you remember our original equation, this k E t, I had written this as kappa square by tau d r to the power 6, then I said this is a constant, right. So, this is should be tau d 0. Now, if I consider this random orientation of this donor and acceptor, then this quantity is also will come inside this constant. So, I will write this as a constant divided by tau d 0 r to the power 6. But remember that this constant has spectral overlap integral within it. It means this is a constant for a definite pair of donor and acceptor. So, this is a constant for a definite pair of donor and acceptor, and that constant is written as r capital R 0 to the power 6. That I can do as per my desire, right. It is written capital R 0 to the power 6. And if you know this overlap integral between this donor and acceptor, and from the expression of this quantity over here, you will be able to calculate the value of R 0, and that value of R 0 is fixed for a definite donor and acceptor. So, the final equation will be K E t is equal to 1 over tau d 0 r 0 by r to the power 6, and that particular constant r 0 is known as Forster distance. That is known as Forster distance. Okay. Now, let me define a quantity which is called the efficiency of energy transfer, denoted by capital E. Right. Let me define and then I will explain what is that. Efficiency of energy transfer is denoted by capital E, which is equal to the rate of deactivation from the excited state to the ground state, right, the rate constant that is leading to the energy transfer divided by the total, right. Like similarly for the quantum field I divided the Kr by Kr plus Knr. For fluorescence quenching, what we had that for the quantum field, that is Kr by Kr plus Knr plus Kq into Q. So, in this case the another pathway which is non-radiative pathway, that means energy is taking out by the system is K capital E t, right. So, in this case the efficiency should be K capital E t divided by the total rate constant, right, and total rate constant means inverse of tau d 0, that means this Kr plus Knr, and then that another rate constant which is responsible for the deactivation is K capital E t, rate constant of the energy transfer. So, this efficiency of energy transfer can be easily written as K E t divided by tau d inverse. So, in this tau d inverse I am going to have this Kr plus Knr, right, because you remember tau d, what to write here, tau d equal to 1 over Kr plus K Nr, right. So, I am going to have this all the time, this plus K E t, right, and you also please remember that this K E t is a function of r, small r. This is the distance between the donor and acceptor, and that distance dependence is very high, is r to the power 6. So, I better write here is a function of r, this is a function of r. So, this is also a function of r. So, efficiency is also a function of r. So, then I can just simply put the expression of K E t r in this equation, right. So, if you do that, so then this will be tau d, so this is again tau d 0 inverse into r 0 by r to the power 6, right, from here divided by tau d 0 inverse plus tau d 0 inverse to r 0 by r to the power 6, right. So, if you just simplify this expression, what you will going to see is 1 divided by 1 plus r by r 0 to the power 6, you will get such kind of expression, right. So, efficiency of energy transfer is something like this. As I told you earlier that if this is my emission spectra, D, in presence of acceptor there is a decrease in the intensity and there is a increase in the intensity of another wavelength, right. Like this. So, here the intensity will decrease and here the intensity will increase. If you monitor the fluorescence intensity at this wavelength and fluorescence intensity at this wavelength, then with increasing of this acceptor concentration, that means the average distance between the donor and acceptor will change, you will get a reduced in the fluorescence intensity, and in this wavelength the fluorescence intensity will increase, right. So, that is also in some other words must be connected with the efficiency of the energy transfer. Suppose you have added some molecule A and nothing happened, right. The fluorescence intensity remains same as without the presence of this acceptor, that means nothing happened. Then the efficiency of energy transfer, if I now may say like that, then the efficiency should be 0, that is it. And let us say for example, you have added this acceptor and the whole complete quenching of this fluorescence, right. There is nothing, it is like this 0 over here and only this guy was like this. It means the efficiency is 100%, right? The efficiency is equal to 1. So, if I now take this efficiency in a scale between 0 and 1, so I can tell this efficiency in terms of the fluorescence intensity in presence of acceptor and in absence of acceptor, that is it. So, if I this efficiency E is typically written as 1 minus I dA by ID, right. So, you see here this efficiency when the IDA, that means the intensity of donor in presence of acceptor is same as ID, that means there is no change in the emission intensity. So, then IDA by ID equal to 1, 1 minus 1 equal to 0, that means the energy transfer is completely inefficient, I mean 0, nothing. Now, if you consider that after addition of this acceptor, the fluorescence intensity became 0, I mean from some value, it could be 100, from 100 to 0 or 1000 to 0, but it was whatever it is, from there it is 0. That means 0 by something is 0, 1 minus 0 equal to 1. So, then efficiency is 1, that means it is a fully efficient energy transfer. Similarly, this efficiency also can be written in terms of the lifetime. In case of energy transfer, this lifetime of this species will also change because of the creation of this additional pathway. What is that additional pathway? That I wrote in just few minutes back as KET, that is my additional pathway. That is why this, when I have calculated the efficiency, right, I have written this KET divided by the total rate constant, right, and that is the rate constant. So, the fluorescence lifetime will also change, right. That means I can write also this efficiency in terms of 1 minus tau dA divided by tau d. So, here this tau d is the lifetime of the donor in absence of this acceptor, and tau dA is the lifetime of the donor in presence of acceptor. Now, you can say that okay, if I increase the acceptor, right, then obviously this will change, this will be different, but the reason is not because you have more acceptor. The reason is that the average distance between the donor and acceptor will decrease. You have a one donor and 100 acceptor, then from donor to the acceptor distance, average distance is something. If you have 1 million, then average distance will be much smaller. So, that is why you are going to have it, because the only thing which is dependent here is the distance, right. And for a definite donor acceptor pair, that R, capital R 0 is a constant, right. So, telling this, now I can simply do one thing. I can make a plot like this, where this y axis is my E and this x axis is my R, and now I can comment on that. right. What will be the value of E, that efficiency, as I change my R value, right, that will automatically come, right. So, what equation I already have? I have this equation involving efficiency of the energy transfer as well as the R, the distance between the donor and acceptor. Here by this way I will going to calculate this efficiency, right, and then here capital E equal to 1 over 1 plus R by R 0 to the power 6. With this I will plot this, right. So, let us take a value when R equal to 0, that small r equal to 0, here is my R, when the small r equal to 0, right. So, is over here. So, 1 plus 0 to the power 6 and that is inverse. So, this is equal to 1. So, this value will be equal to 1, and when R equal to R 0, right, let us say take a point over here where this value of R equal to R 0, right. In that case this R 0 by R 0, that means 1 divided by 2 equal to 0.5. So, here I will get 0.5, here is my point and here is my another point, and when R equal to twice R 0, then this twice R 0 divided by R 0, that means 2 to the power 6, that is 64, the 1 divided by 65, that will come about 0.015. So, it is almost over here, and in between if you plot, the value will come, what we are going to see, the plot will something like this, right. So, from here I can at least tell that when the efficiency of energy transfer is just 0.5, that R is equal to capital R 0, which is my first touch distance, right. Okay, so, let us finish here and we will continue our discussion on the next day. Thank you very much.